Hello everyone. I welcome you to this second lecture of ARIES lecture series. We'll discuss on optical telescopes today for about 1 hour, and then we'll take up some questions. Of optical telescope, then we'll discuss what is the purpose of this telescope. Then going through active optics technology, which is the modern day technology, and then at the end we'll discuss about performance factors of optical telescopes. So basic features, let us discuss. So there are two types of optical telescope, as you all know. So one is a refractor telescope, where incoming light comes falls on this objective lens, and then it focuses at the focal plane, and then it is regarded by some detector. So from this objective lens to this focal plane, this distance is called the focal length of the objective. This objective lens could be a lens, could be a set of lens, or could be mirrors, could be set of mirrors. So in case of mirrors, it is called the refractor telescope. In the lower picture you see, here the incoming light falls on the mirror and then again focuses at this focal plane. Yeah, these there are two very important parameter of a telescope. One is the f number. So this f number is basically ratio of the focal length and the diameter of objective lens. So in this case I have taken example of 25 millimeter, and 5 millimeter is the diameter. So this f number is 5 in this case. So this f number is also called f ratio of a telescope or speed of a telescope. We'll discuss more about this in later slides. Now another important parameter for an optical telescope is a plate scale. This basically tells uh, 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 what is the relation between the angular separation of two objects which we are imaging, and the linear separation between those two objects at the image plane. So this is basically unit angle which is getting imaged at the focal plane. So you see 1 radian by the focal length, and 1 radian equals 265 arc second per focal length. Focal length is normally expressed in millimeter. So unit of plate scale is arc second per millimeter. Now I is also an optical telescope, and this is a refractor telescope. What you see, light rays are coming from infinity, and they are focusing at the retina over here. So right image, how image forms, it is shown over there. So there is very important aspect. The aperture diameter of our eye is 5 millimeter, as you see, and for a normal light, and you see the focal length between this lens and the retina, this distance focal length is 16 millimeter. So if you determine the f number of our normal eye is at 3.2, but when you go to a room and where there is a lot of light, it's a bright room and we want to see the object, then the pupil of our eyes gets reduced. So it becomes 2 millimeter. So but the focal length remains same. So in this case our eye becomes f8. Now when you go to a dark room and try to see objects, then there our pupil dilates. So that becomes roughly 8 millimeter in size, and f number becomes f2. So you can see the focal length of our eye actually does not change, but f ratio, I mean the speed of our eye changes. Now I pose a question here, very basic. What is the field of view of our eye? You can think over it. Well, we usually, after the image is formed, light is collected by this objective, either lens or mirrors. So image is formed the focal plane. Normally, if you want to see what this big objective sees, then we put an eyepiece. Here is the negative eyepiece is put, and this is before the light focuses, and then finally the outgoing beam goes to our eye. And so capital F is the number, I mean the focal length of this lens, and small f is the focal length of this eyepiece element. And similarly, in another case where we use positive eyepiece, so these numbers are shown over here, and there's a angle alpha and beta. Alpha is the angle found by this objective for that object, and beta is that what is seen by your eye. So we define a term magnification. Magnification is nothing but a ratio of the focal length of the objective by focal length of the eyepiece, or this angle beta by alpha. Now this is very important to know. Typically there are two kinds of telescope we refer to, and one is the fast telescope, where the beam is converging very fast from the objective lens, and another is a slow telescope, where from the objective lens beam is converging very slow. So this fast telescopes actually make a wide light cone, and these telescopes are having wide field of view. These are low power short telescopes, but these telescopes are very good for survey work. You can cover very many celestial sources at a time. Many galaxies, nebulae, and star clusters you can cover and study. So any large wide field study, large scale study of objects are done with these fast telescopes. For example, at ARIES we are having these three telescopes. These we refer as a fast telescope. One is half meter Schmidt telescope, this is f1. Then 4 meter liquid mirror telescope, it is f2. Then 1.3 meter fast optical telescope, this is f4. Now we also, if we want to study in detail, then we need a slow telescope. So this has a narrow field of view, and it is high power and small field observing it is used. It is good for stars and galaxies when you want to study in detail. So for example, 3.6 meter Devasel optical telescope, it has a f ratio of 9, and 104 centimeter Sampurana telescope, it is f13, and 15 centimeter solar telescope, it is f ratio of 24. You remember the eye, in case of eye, it can change the f ratio from f2 to f8. So now this is a very important slide, the image degradation or aberrations of an optical telescope. So what happens actually? So light from objects coming from infinity, they falls on this objective, whether it's a lens or mirror or optical system, and then this wavefront focuses the focal plane. So a single point focuses, very sharp images is formed. I mean, one representative image is shown over here. This is a very well focused image. But if there is some degradation factors which are basically could be due to optics which we are using, or due to atmosphere, or could be due to any other reason, then our wavefront is getting aberrated. And from the ideal wavefront, the deviation, we refer it as error. So we call it this reflects in a spread of focus at the focal plane. You can compare this image. This is a little out of focus image. This is not as sharp as the top one. So this wavefront error, we call it. This is basically difference between ideal wavefront and aberrated wavefront. And there is two notations we use: peak to valley of this and RMS root mean square wavefront error, and this we measure in the unit of lambda, that is length. So what are the sources which degrades the ideal wavefront? So there are some intrinsic sources we will discuss about, and there are two categories in this. One is the chromatic aberrations, another is the monochromatic. These are 5 in numbers. These are also called Geidel aberrations. Then there are some induced aberrations. These are alignment errors. For example, if this optical system contains many optical elements, then if they are not properly aligned, that also reflects in degradation of wavefront. And second is the surface deformation, because when this optical system we use, we mount it at certain place, their temperature changes, and also when this telescope moves, then the optical elements also change its position, so gravity effect is there. So these surface deformation of optical surface also induce error. This is called induced errors. Then third is the earth atmosphere, because the earth atmosphere there's a change of refractive index and turbulence in earth atmosphere, that is also a cause. This also falls under induced category of wavefront degradation. Now image quality criteria for an optical telescope we'll discuss. So what you see is basically, so the point sources, when we image them at the focal plane using a camera, then two-dimensional images form, x versus y, and this y-axis is the intensity. So this two-dimensional profile of a point source formed at a focal plane of a telescope, this actually we refer when we discuss intensity distribution of this profile as a function of radius, then we call it a point spread function. So PSF is a very important parameter when we discuss about image quality criterion of an optical telescope. So what a true PSF is? So basically the true PSF is convolution of four factors. This original star image, I mean the nature of original intensity profile of stars with a point source or extended source. Then it is convolved with the atmospheric distortion by Earth atmosphere, change in refractive index, and also the turbulence parameters. And this area diffraction profile, which is which we form by optics, which we use. And then the third is the aberration or deformation in alignment and intrinsic aberrations of these optics. So true PSF is a convolution of these four factors, and what is shown over here is basically in this diagram, this is a 3D PSF of an image. So this is a profile, a peak, and the profile comes down. So this is the radius versus intensity if you plot. So this is the PSF. It comes from unit 1 to down, and so this is encircled energy. I mean in radius, the percentage of encircled energy plot is formed over here. So any single measure is very difficult to assign when it comes to the image quality criterion, but there are two measures that they stands out. One is the full width at half maxima of this PSF. So this is one intensity. When it falls at 1, this is half width. In fact, the full width at half maxima of this particular PSF profile, that represents image quality of an optical telescope. Second parameter, we call it the 80% of the energy diameter encircled in this. So 80% energy, if it is encircled in a diameter, that we refer as the E80. So normally while designing optics, we use that parameter. But assuming that our stellar PSF behaves like a Gaussian, then full at half maxima of a PSF is 2/3 of this E80 parameter. So these two are very important parameter. We will refer these in our lecture. Now let us discuss one by one the intrinsic aberrations or deformation which can happen to our images. So this is a chromatic aberration for a lens. So this is diameter for 25 millimeter diameter and f4 telescope it is mentioned. You just see. So this chromatic aberration arises because the lenses have a different refractive index for different wavelengths. So 3 wavelengths are shown over here. You just see. This is a blue wavelength. Blue light is focusing over here. The green light is focusing over here and the red light is focusing over here. So when you see a 2D projection, I mean at the image plane, then it is 1 millimeter diameter. This is shown, and all these three lights are seen. I mean the energy conservation is shown over here. So 1 millimeter diameter is very high. It is 1000 micron diameter we are talking about. And our aim would be to minimize this energy concentration in as small diameter as possible. So we use achromatic doublet. In this case, we can use the doublet to remove this. So this is the images stepping through this focus when you go away out of focus. So this is a focused image, and so 1000 micron diameter is basically reduced to a 50 micron diameter using doublet. So this is how chromatic aberrations are removed. And you see, for a single light, it is reduced in a 10 micron diameter. Now this is another aberration. This is a spherical aberration. These are all monochromatic aberrations. So for a mirror, if you see, and this arises because of peripheral rays which are sitting at this peripheries, they have a short focus. This is a peripheral rays, and the paraxial rays, they have a long focus. So that is why because of this you get a diameter circle of least confusion. This is typically for a particular lambda. This is 13 micron. And this is spherical aberration. Actually, this goes with the f number of telescope, and also with the diameter by focal length power cube. So we can remove spherical aberration using a parabolic mirrors in case of mirrors. So you just see this is the images found by the parabolic mirror, and this is the focused image. This is out of focus image inside. This is out of focus image outside, and the squares are 30 micron. You see this is square. So you can see a very sharp image using parabolic mirror, but using spherical mirror it is not so sharp. So this is used for 8-inch telescope f8, and it is this demonstration is shown at for 550 nanometer. So you can see we are plotting the point spread function with this particular optics, no error. So for a spherical mirror, we are getting this PSF, which is having a Still ratio of 0.7. Still ratio is basically the ratio between aberrated wavefront intensity and the ideal wavefront intensity. You can see this factor is 0.7 over here. In parabolic mirror case, this is unit. So you see, using the parabolic mirror, we get rid of spherical aberration. Now coma, this is the second monochromatic aberration, and this is off-axis aberration. This happens when our incident wavefront is tilted or decentered with reference to the optical surface. So what you see here is basically this optical surface, and this in yellow there are different zones are shown over here. So different zones actually they form different images, and finally they take a shape of coma. So that is why it is called the chromatic shape. And since this different zones are tilted with reference to the optical surface, so this angle is referred as alpha. So you can see this chromatic aberration is equal to alpha into d by f square. Now this is the third monochromatic aberration, astigmatism. This is again off-axis aberration, and this arises because of the projectional asymmetry of incident wavefront onto the optical surface. And you see, there are for radial and tangential images, there are sharp focuses are at different locations, and when you go away from the circle of least confusion, I mean from the focal plane, a little away and little other side, then you get this kind of images. So this astigmatism actually is proportional to alpha square. I mean it's much steeper with reference to alpha than coma, which was with goes with only with the angle alpha. Now there are this fourth and fifth monochromatic aberrations. First one is the field curvature. This is again off-axis aberration. This goes as alpha square. So this aberration actually, since this optical, it arises from the optical element. This is a intrinsic property. Arises out of the curvature of these optical elements, and hence our images formed are having curvature. So this becomes more prominent when you are looking at a wide field. For example, if you are looking imaging half degree size object, for example the moon in the night sky, so you need to take care of this field curvature. But when you are interested in a very small field of view, these are not that dominant. Now distortion is another aberration, and you can see so distortion goes as alpha cube, and so this is undistorted image. So in fact you can see this. So in distorted images, plate scale actually is not same, it varies with your at the image plane. This is again when you are interested in wide field like moon and larger size object, degree by degree field. If you are interested in a fast telescope, probably you have got to correct this field curvature and distortion effect by introducing more optical elements or corrector elements. Now we come to the telescope configurations. So this reflectors, what you see here is a paraboloid primary mirror, and there is a secondary mirror, and it is focusing to the image plane or eyepiece, and light coming from a distant object. So reflectors are favored in comparison to the refractors, because they are not having any chromatic aberration, no spherical aberration when you are using paraboloidal mirrors, and mirrors can be supported at the back. Of course, this is a tube, the mirror is lying at the back, so it can be supported. And there are improved techniques for making this mirrors, aluminum and glass and liquid mirrors can be made. So first reflector, it was fabricated in 1668. I mean, you can see this is of 1 inch size. So there are Cassegrain configuration of reflector. So in this configuration, we use primary mirror as a parabolate, and secondary mirror as a hyperbolate surface, convex, and light focuses at the end. We usually make a hole in this configuration. So this is the focus. So this is the most favored optical telescope configuration for large research purpose telescopes. Here secondary mirror has a narrow beam, narrow cone, and as a result you get a very large for effective focal length. So this is used for small field and sharp focus when you want a sharp focus. Now Ritchey-chretien configuration, this is used in modern telescopes. In fact, all the telescopes at ARIES, they are having Ritchey-chretien configuration. In this configuration, primary mirror is a concave hyperbolite, and secondary is a convex hyperbolite, and then there's a hole at the center. So one good thing of this configuration is your coma is removed. So in a way, by using this Ritchey-chretien configuration, you are taking care of spherical aberration, you are taking care of coma. So these two main aberrations are taken care in this configuration. So now there are, if you are interested in wide field, as I said, then you go for a faster telescope, and these telescopes are called Schmidt telescopes. So here you have a correcting plate at the front. I mean, before light enters the primary mirror, and then focuses the detector. This is again curved image surface. So whenever you are interested in half degree field of view or a degree field of view, or even larger few degrees field of view, then we usually use this Schmidt telescope configuration, and we employ, I mean, this we correcting plate to correct the aberrations. Now, the second part of this lecture is will focus on purpose of optical telescope. So there are two important purposes, and first is of course the light gathering power. So as you can see in this picture, because this is a picture of a celestial source. This is a galaxy, and there is two stars, or maybe this one is a galaxy. So you can see more light. You can see when you are having a objective, increase the size of objective. You can see more light, and brighter this object. These two objects are brighter. So light gathering power, when you say A, so this you can write it. It is directly proportional to area of objective lens or mirror. So capital D is the diameter of telescope. S is the diameter of pupillae, D by S whole square. So area and multiplied by 3. This is the losses due to optics and detector. So you can see if you take a 4-meter size telescope and compare with the size of our eye, which is 5 millimeter is the pupil size, 5 millimeter, with compared with the 4000 millimeter, then you get 25 into 4 times the photon. I mean, much more light you will be able to collect. Now coming to the signal to noise ratio of a source at a particular wavelength, then this is proportional to basically directly to area. And of course, T is the exposure time. I mean, how long you expose, collect those photons. That we'll discuss later. So, the signal to noise ratio is inversely proportional to the angle, solid angle formed by the image and this noise, the sky background. This could be due to, I mean, dark sky with very less noise we have. The sky with the moon, we have a very high background, and so this is how sky brightness it is inversely proportional signal to noise ratio. So light gathering power is the most important parameter, to increase. So this is how, uh, the astronomical community have fabricating telescopes, optical telescope with a larger and larger diameter. So y-axis is the aperture diameter of optical telescope, and x-axis is the year. So you can see we started with the Galileo telescope, maybe 1 and 2 inch optical telescope, while we kept on increasing. You can see this is the Herschel 48-inch telescope, which came in 1800 AD. Finally, this is a Keck telescope, 10-meter aperture telescope, came very recently. Now we are planning 30-meter optical telescope by 2030. So we kept on working on this aperture of optical telescope, and this is a very important parameter. Now, second parameter is the resolving power of a telescope, and this is basically also referred as the solid angle formed by the image. So this in a way indicates our ability to see very fine details of any optical image. So these are limited by two factors. One is of course the diffraction limited formation of the image, and this is so we define a sort of Rayleigh criterion, and if angular size of this images formed by the optics is 1.22 lambda by d. So you can see, so this is the Rayleigh limit, which is referred to these two sources, nearby sources, with the ability we are able to resolve them. So in case of our eye, if you see, so this ability, this if you convert this at 550 nanometer, then this becomes 14 arc second per by d, if you d take in centimeter. So in case of our eye diameter, if you 2 to 9 millimeter in this range, so the typical resolving power of our eye is 15 to 90 arc second. So when we say the resolving power, then we set a sort of criteria that is called the Rayleigh criteria. So if there are two PSF which are formed, ARIES pattern which are formed, and the separation of peak is 1.22 lambda by d, then we say that these two sources are resolved. So this is the ARIES disk diameter, this 2.44 lambda by d. So typically FWHM of a single PSF over here is typically 1.03 lambda by d. So here in right hand side, these two sources are not resolved because they are separated by, of course, a lambda by d. So these are not resolved, and these are within the, short of, this is called the depth or diffraction limit, within diffraction limit. But if you are separated by 1.22 lambda d, we say that it is resolved. These are resolved. So this again, this diffraction limit in case of our eye, it is 15 to 90 arc second. So this can be minimized by using a larger size objective. As we discussed in the previous slides, that purpose of telescope is collecting more light. In addition to collecting more light, we also increase the resolving power of telescope by increasing this size diameter. Now the second factor that is resolving power depends is environment. Basically, this telescope images are degraded by blurring effect of atmosphere. You can see in this picture, there's a plane parallel wave front is falling above Earth atmosphere and is getting distorted. So this distorted wave front, we are actually focusing, collecting by optical telescope on ground. And you see this. So this can be minimized by placing the telescope on a mountain hill with a very smooth laminar flow of air or in space. We'll discuss both these aspects. So in fact, we try to go to, try to characterize the site, hilltop, for their goodness, for to establish an optical telescope, how smooth laminar flow of the air is there. So one of the best excellent sites, they're characterized by this single parameter, that is we call the seeing disk. This is in arc second. So typically at visible waveband 0.5 micron. This the best sites, these are, the seeing is of the order of 0.5 arc second, and at infrared waveband it is 0.33 arc second. So these are the best sites we have. But a typical astronomical site has 1 arc second seeing at the ground level. Now this slide is basically to demonstrate how this blurring of images happens due to air temperature in homogeneity, so which we call seeing. So this is an optical element. So your light is passing through this. So we are creating a sphere of air which is 1 degree centigrade cooler than the surrounding air. So then it is passing through a perfect lens, and what we get here, in x-axis is the radius in arc second, y-axis is the relative intensity. So immediately you get a half arc second FWHM image. So this is the profile, through this resulting image. So if suppose this temperature difference is more than 1 degree centigrade, this profile will be larger. PSF will be maybe 1 arc second, 2 arc second. So you can simulate, we can simulate and see. So this is how, due to air temperature in homogeneity in the light path, our image gets blurred. So again, the resolving power of telescope, how we have improved through year. If you see at x-axis it is year, it is 1480 and 1600, 1800 and 2080. So on y-axis it is the resolution in arc second, it is referred. So angular resolution achieved by our telescope. So initially by 1609 AD, when Galileo discovered a 5 centimeter telescope, saw the celestial sources, our resolving power was limited by human eye, and you can see it is somewhere here. We cannot resolve even the surface of Jupiter or rings of Uranus with our bare eye, which we cannot resolve. Even craters of moon we cannot resolve with our bare eye. But the Galileo telescope can resolve it very well, because the moment you are having 2-inch telescope, your resolving power becomes 10 arc second. The moment you are having higher telescope, your resolving power increased. It is up to 1 arc second. Palomar 5-meter telescope, it is having close to 1 arc second resolving power. Then this is the typical limit of a ground-based facility, that 0.3 to 0.5 arc second. That is the best seeing which we can get from a ground-based optical telescope. Then it is limited by Earth atmosphere. So to pass that, we go to air, above Earth atmosphere, and we try to set up some space telescope. That is how Hubble Space Telescope, it was set up with 2.4 meter aperture. We'll come to this again. So you just see, this is the difference. This is the This is a picture of a globular cluster M15 taken with a ground-based facility, and this is the high result. I think both the pictures are taken with SST. Just zoomed in picture of the center of image is shown over here. So we are able to gain in resolving power by a factor of 10 in comparison to the ground-based telescopes. Now the third component of this talk, we will focus on active optics technology. We will see that how active optics technology has improved the image degradation due to optics, because that is very important. Degradation. Now, active telescopes, how they came into being, because uh, before 1989, I would say, since 1609, most of the telescopes, I mean all the telescopes, they were conventional telescopes. They were called passive telescopes. For example, 104 centimeter Sapuran telescope at ARIES, 1.3 meter optical telescope, which are set up in very recently 2010. This telescope at ARIES, they are all conventional passive telescopes. Even 2.3 meter Vanubabu telescope at Kavelur in India, that is also conventional passive telescopes. So these telescopes are maintained or modified by offline adjustment of primary and secondary mirrors and their adjustments. But the modern telescopes, which are larger than, let's say, 3 to 4 meter class optical telescope, I would say, for example, European Southern Observatory New Technology Telescope 3.5 meter, which was installed in 1989, that is active optics telescope, and our recently established 3.6 meter optical telescope at Devasthal, which was commissioned in 2016. This is also active telescopes. So here what happens, the image quality is monitored online and corrections are made automatically, which is not possible in these conventional telescopes. So now when you talk about the primary mirror objective lens of this telescope, their size, I have compared two telescopes. One is 1 meter ARIES telescope, another one is the 3.6 meter ARIES telescope. So diameter in 1 meter case, it is 104 centimeter, 1040 millimeter, and 3700 millimeter. Thickness is 150 millimeter, and in first case, and second case it is 167 millimeter. So if you take ratio of thickness to diameter of these two telescopes, so in this case 1 meter telescope is 1:7. So, and in this case it is 1:22. This is very important because thickness to diameter ratio is very high, and this is why, that is why we are able to deform this primary mirror of this telescope by using artificial forces. Now these are the passive telescopes, and their limitation we will discuss. So here I will describe a telescope which are having 3.6 meter aperture, and encircled energy E80 parameter specification is 0.27 arc-second. So parameter wise is very good as for even this telescope. The optical specification is very good, 0.27 arc-second. But when you optimize this telescope in a different direction, for example, this is zenith direction, then we optimize various aberrations, 0, 1, 2, 3, 4, 5, various aberrations, optimization is on, and we achieve this to 0.27 arc-second in this passive telescope. When you optimize this parameter in the south direction, you again achieve it, west direction you again achieve it, east direction again. But in this telescope it is very difficult to retain this 0.27 arc-second E80 parameter with different direction, because these adjustments are made offline by placing the telescope in a certain direction and not online. So this is a major limitation of passive telescope. Now now coming to the active optics system. So active optics technology actually, you just see this is a picture of two mirror optical telescope. So this is the primary mirror telescope, which is having a aspect ratio, thickness to diameter ratio of roughly about 22. So it's a very thin mirror telescope, and this is the secondary mirror hyperbolite telescope. So what happens when light falls on this, it goes to secondary and again comes back. So we collect this light by introducing a mirror in between to a wavefront sensor, and here this wavefront sensor analyzes that light, and it goes to the computer. Finally it finds a correction and gives a feedback to these actuators, which are mounted with a back into the primary mirror and also the secondary mirror adjustments. So this is how this active loop works. So what it does actually, it maintains the desired shape of the primary mirror in this way, and maintains optical collimation of this two mirror system against the deformation caused by gravity. I would say when you point this telescope to different direction, let's say zenith and let's say east direction, then your secondary mirror will be looking to the east, and this mirror will go a little up. So with gravity, the secondary mirror comes a little, will deform. Come with gravity, it come a little down. So the primary and secondary mirror again need to be adjusted to make it align. So these kinds of gravity deformation, and also the temperature, because during the night your temperature changes, and the thermal expansion in primary and secondary mirror happens, so that adjustment is also maintained, and also due to wind. So all this deformation happening to the image of a telescope, these are corrected through this active optic system, and such large telescope actually cannot function without this active optics. So let us briefly step by step see to what actually this does actually. So in this particular case, our 3.6 meter Devastal optical telescope, we have a active optics technology. So of course this primary mirror is partly deformable, not fully deformable as in the case of active optics telescope, where aspect ratio is even more high. So this rests on 69 force actuators, which provide necessary stress force on mirror, so that the mirror is always of the required shape, and secondary mirror rests on 6-axis motion stays. So 3 in translation, x, y, z, and 3 in rotation. So there are 6 stays, motion stays is possible to do in secondary mirror. So amount of correction forces are calculated through feedback mechanism, as I told earlier, using a wavefront sensor, which again we measure from a star light, and these corrections are applied in real time. Typically these corrections are applied one correction every 10 seconds. In fact, there are two label corrections. One is the open loop corrections, which we know with altitude, particularly the gravity corrections, which are applied every second. So with a rate of 1 hertz, we apply this open loop correction, and then there are closed loop correction that we measure wavefront. We try to get the measurement and the deviation from the original wavefront, and we try to calculate the correction. That correction is applied every 10 second or 20 second or even up to a minute. So that is called the closed loop correction. Then these actuators are actually very precise devices. These are capable of providing forces in the steps of 0.2 Newton. So typically if you see, so 0.2 Newton force makes a distortion on the primary mirror, and it is roughly of the order of 10 nanometer. So that is the kind of correction we are able to do using this active optics online. So now this is very important when we see, when we want to achieve seeing limited observation from an optical telescope, then this optical telescope actually the image degradation of this optical telescope or image aberration should be as low as possible, in fact much lower than the seeing degradation, which is not in our hand. So for example, this active optics technology actually has come up in this technology came in the year 1989, and this actually this was a revolution in ground based direct imaging, optical imaging with optical telescope. So what we see here, we represent a we have taken a astronomical site where typical seeing which we achieve is zero point 0.3 arc second. So this is the first picture. This is a 12 arc second by 12 arc second picture of Omega San, the center of a globular cluster. And so you see with the Schmidt telescope, where you can get FWHM of 2 arc second. So you can see your seeing degradation is much less, but FWHM is basically is the image degradation by optics and telescope alignment errors. In this red circle shows that how image looks like. Now coming to the item 2, this is again 4-meter class optical telescope, but a passive telescope. Here we are able to achieve FWHM of 1 arc second. I mean, if we maintain the adjustment on this passive telescope to the best possible limit, it's very challenging to get even 1 arc second. Compare this to with the seeing of this particular site. Now coming to the active optics telescope, with the same image, you can see all these 3 stars are separated over here with this active telescope, and here we are able to get full width half maxima of a PSF 0.33 arc second. So you can see this is a pretty close to the seeing of that site. So these are called the seeing limited observation from an optical telescope. And of course, with the advanced computer technology, I mean, we can still process, and if you want to see some more features, I mean, it's possible to achieve FWHM for certain images of 0.18, but particularly the good signal to noise ratio, we would be able to achieve FWHM of 0.18 arc second. Now, this is the last part of this lecture. This is we will discuss about performance factors. So again, the same equation, the short of performance outlook slide I have kept. So you can see the signal to noise ratio of any source, whether it's a point source or extended source, is proportional to the time over which we expose that particular image with this optical telescope and detector. And this is the light gathering power, light collective power of a telescope. And then this the noise part, basically signal to noise ratio, is inversely proportional to the image FWHM PSF. This is all related, epsilon, angle formed by the image at the focal plane multiplied by the sky, I mean background or the noise. This noise can also be due to CCD detector and also the sky. So you can see if we are taking imaging with a 4-meter class optical telescope, and if we are able to get images which are having PSF of half arc second, let's say 0.5 arc second, then this is at par with the 8-meter class optical telescope getting 1 arc second PSF. Now again, this 4-meter optical telescope with 1 arc second is compared. This is as good as 8-meter optical telescope with a 2 arc second images, and 2-meter telescope with a half arc second images. So this is the third case I have taken. 4-meter optical telescope, it is giving you PSF of 2 arc second. Then this is as good as 2-meter optical telescope with 1 arc second images. PSF, and 1-meter telescope with half arc second. So it depends on us that how we want to use our telescope. So it is very important to keep our telescope aligned using online tools, using active optics technology, so that we can use the telescope to the best of its capacity. Now this is one slide where some known double stars with known separation we have imaged with a 3.6 meter optical telescope at Devastal site in India. So you can see here there are 3 images. So this is these two images of stars. They are very well separated. They are separated by 1.2 arc second. So here there are again two stars. They are separated by zero point 0.6 arc second. And here there are two stars that are shown by zero point 0.4 arc second. So we imaged several stars, double stars with a known separation with this 3.6 meter telescope, and these are the contoured profiles. So you can see the best images. I mean, this telescope has a capacity to resolve stars which are separated by 0.37 arc second, and this we calculated that this is the effect of seeing. And of course the tracking comes into the play because you expose this, the tracking factor is coming. How can I go back? Okay, so this tracking factor is coming from this time, because you'll be exposing the images with a certain exposure time, and the telescope has certain tracking errors, and this optics degradation, of course the alignment errors and intrinsic aberrations, they all come together. So if you run this all these errors in quadrature, so probably it is possible to get images of the order of zero point 0.3 arc second. And with this telescope we are able to achieve in this way the seeing limited observation from ground based facility. Yeah, so this is all for today's lecture. Thank you very much. So I will take questions which have come online. So this is first question by Utkarsh Mishra, and who has asked that what is the SQM of ARIES observatory skies? How do we calculate sky brightness limit of our telescope? Well, this sky brightness is for any site is calculated using CCD camera, which can image the stars and sky both, and then we take standard stars which are calibrated. The flux of those standard stars are calibrated. Usually, this sky brightness we measure in the dark night at zenith to get a limit of achieved from a certain website. And I think there are papers on 3.6 meter dot telescope. You can have a look at this parameter, that what is the sky brightness limit. So that is first question. Now second question is by Pankaj, who is asking that how the space telescopes Hubble are different from ground telescope. So as I stated in the lecture that uh, the image degradation due to Earth atmosphere is absent in telescope which are put in space. For example, Hubble Space Telescope, and the resolving power of these telescopes are limited by diffraction, and Rayleigh criterion 1.22 lambda by d is directly applicable to these telescopes. So in general, the space put in the telescope put in space is about 10 times better in terms of resolving power than ground-based telescope. So it means the 10 times sharper images the space telescope will form in comparison to the ground-based optical telescope. Now this is there is a third question. This is by Sarwan Kumar, and it is asked that which kinds of telescope can be used for a science outreach program and for simple observational experiments of the solar system for MSc students? I think this is a good question. That where to start with? I think most of the for science outreach program, we normally we focus on planetary objects and comets and some nearby stars, bright stars. I would say that any telescope which is having a aperture of 10 to 11 inches is good enough for these observational experiments or MSc students program. And yeah, so this was the third question. Now I'll take the fourth question. This is by Mr. Gaurav Singh Raghuvanshi, and he's asking, please discuss more about space telescopes. Here I mainly focused about ground-based optical telescope and how we use the active optics technology to align or reduce the image degradation from this ground-based telescope to get sharper images. In fact, our main aim was to get as sharper images, as it is possible with the space-based telescope. In fact, HST, Hubble Space Telescope, has a resolving power of roughly zero point 0.1, close to zero point 0.1 arc second. And in fact, from using active optics technology from ground-based telescope, it is very much possible to get uh, images as sharp as zero point 0.3, zero point 0.4 arc second. So it's pretty close. So I think detailed discussion we can have in other lecture, which is totally devoting on a space-based optical telescope, which I can cover. Now I will take the next question. That is fifth question. It is by Sekhar Shinha. What is gravity correction? So yeah, gravity correction actually uh, a typical optical telescope reflecting telescope professional is a two mirror system. So it is a primary mirror and secondary mirror. Both the mirrors are mounted in a tube. So what happens when this tube moves from one direction to another? Let's say it is moving from zenith to the east direction to point another object. Then what happens? This the secondary mirror is mounted and the primary mirror is also mounted. So due to gravity, there is little displacement in the primary secondary mirror position along with its mount because it's heavy, and there is little displacement in the secondary mirror also. So to correct this displacement and ensure the collimation of primary and secondary mirror, what we do, it depends on altitude. So or the gravity. So this is why we call it a gravity correction, because at different altitude, your effect of gravity will be different on this primary and secondary mount, because they carry mass. So this is answer to your question, that gravity corrections are taken care. Now there is another question, sixth question I would say. This is by Kamlesh Kushwaha, and it is asked that what will be the maximum separation what we can measure from Earth. Uh, yeah, this is question is not very much clear. What I would guess is that the separation of stars being referred over here, I would say it is a minimum separation which is observed from Earth for any two point sources. That is as good as 3.2 arc second. The best observing site, optical observing site at Earth, it is of that order. Yeah, so there is one more question. Can we image long exposure images using active telescope only by deforming the primary mirror instead of rotation the telescope for compensating Earth rotation? Actually, when there are a couple of things which are mixed here. When we talk about long exposure images, uh, that happens on a detector, on a CCD camera. So that is the task of a telescope is basically to keep the images at the same point and as sharp as possible with a well aligned telescope. So keeping the images at a single point, actually that is linked with the tracking error of a telescope, and we use guiding for that purpose. And we image from the off axis field, we image a star, and using position of that star we guide the we give a telescope a guiding error feedback. So that way telescope keeps pointing at a certain object. So the tracking error and the guiding is one issue that happens independently, and parallelly it also happens that the telescope keeps taking the images and try to measure the wavefront wavefront images online, and try to keep it as sharp as possible. So that is image quality, online image quality corrections that is also made. And with regard to the earth rotation effect, that is already taken care, because when telescope tracks, it tracks in all the, this is by the way, there are equatorial and ultra azimuth telescopes. In both the telescope, there are actually they move and try to track the objects. So this is the answer of your question. Okay, so thank you very much for joining to this second lecture. Thank you. Those who missed the lecture can find on YouTube and Facebook. Yeah, so those who have missed this live lecture today, it is online on Facebook and YouTube. You can go there and links are available on the site. Thank you.